Our next lesson is on sample means, section 7.3. In this section, we'll find the mean and standard deviation of the sampling distribution of a sample mean. We'll calculate probabilities involving a sample mean when the population distribution is normal, and explain how the shape of a sampling distribution of sample means is related to the shape of the population distribution. We'll also learn to apply the central limit theorem to help find probabilities involving a sample mean. Sample proportions arise most often when we are interested in categorical variables. When we record quantitative variables, we are interested in other statistics, such as the mean, median, or standard deviation of the variable. Sample means are among the most common statistics. Consider the mean household earnings for samples of size 100. Compare the population distribution on the left with the sampling distribution on the right. What do you notice about the shape, center, and spread of each? The histogram below shows the distribution of stolen bases for the 1,341 Major League Baseball players who had at least one plate appearance in the 2009 season. The right tail of the histogram actually extends to 70, but we cut off the scale at 20 to be able to focus on the majority of the observations, which are near 0. Next, we have a histogram showing the distribution of the sample mean number of stolen bases for 100 simple random samples of size n equals 45. It is graphed on the same scale to make it easier to see the difference in variability. In addition to being much less spread out, the distribution of it is also much more symmetric than the population distribution. However, the center of each distribution is really about the same. When we choose many simple random samples from a population, the sampling distribution of the sample mean is centered at the population mean mu and is less spread out than the population distribution. Here are the facts. Suppose x bar is the mean of a simple random sample of size n, drawn from a large population with mean mu and standard deviation sigma. The mean of the sampling distribution of x bar is mu of x bar equals mu. The standard deviation of the sampling distribution of x bar is sigma of x bar equals sigma over square root of n, as long as the 10% condition is satisfied. These facts about the mean and standard deviation of x bar are true no matter what shape the population distribution has. When we choose many simple random samples from a population, the sampling distribution of the sample mean is centered at the population mean mu and is less spread out than the population distribution. Here are the facts. Population mean mu, we have simple random samples of size n. For x bar, we get values of x bar. In this case, we have our mu and sigma over square root of n. The Greek and Roman symbols all have specific and different meanings. Either use notation correctly or don't use notation at all, in which case you must describe it in words. Suppose the number of movies viewed in the last year by high school students has an average of 19.3 with a standard deviation of 15.8. Suppose we take a simple random sample of 100 high school students and calculate the mean number of movies viewed by the members of the sample. What is the mean of the sampling distribution of? What is the standard deviation of the sampling distribution of? Check whether the 10% condition is satisfied. Here is our solution. The mean mu of x bar equals mu, which is 19.3. The standard deviation of the sampling distribution, sigma of x bar, equals sigma, which is 15.8, divided by square root of n, which is square root of 100 or 10, which equals 1.58. The 10% condition is met because there are more than 10 times 100, which equals 1,000 high school students. We have described the mean and standard deviation of the sampling distribution of the sample mean x bar, but not its shape. That's because the shape of the distribution of x bar depends on the shape of the population distribution. In one important case, there is a simple relationship between the two distributions. If the population distribution is normal, then so is the sampling distribution of x bar. This is true no matter what the sample size is. Suppose the population is normally distributed with mean mu and standard deviation sigma. Then the sampling distribution of x bar has the normal distribution with mean mu and standard deviation of sigma over square root of n, provided the 10% condition is met. The height of young women follows a normal distribution with mean mu equals 64.5 inches and standard deviation sigma equals 2.5 inches. Find the probability a randomly selected young woman is taller than 66.5 inches. Let x equal the height of a randomly selected young woman. Z equals 66.5, which is what we want to find, the probability they're taller than, minus 64.5, which is the mu, the mean, divided by 2.5 standard deviation. We're finding the probability x is greater than 66.5 or z is greater than 0.8. To find greater than, we always take 1 minus the distribution we look up on the A table, which is 0.7881, and which equals 0.2119. The probability of choosing a young woman at random whose height exceeds 66.5 inches is about 20.21 or 21%. Find the probability the mean height of a simple random sample of 10 young women exceeds 66.5 inches. For a simple random sample of 10 young women, the sampling distribution of their mean height will have a mean and standard deviation. Mu of x bar equals mu, which is 64.5. Sigma of x bar is sigma divided by the square root of n, which is 2.5 over the square root of 10, or 0.79. Since the population distribution is normal, the sampling distribution will follow a distribution of n 64.5, 0.79 distribution. Z equals 66.5 minus 64.5 divided by 0.79, which equals 2.53. The probability x bar is greater than 66.5 is probability of z greater than 2.53, which is 0.0057. It is very unlikely, less than 1% chance, we would choose a simple random sample of 10 young women whose average height exceeds 66.5 inches. So here's just a regular distribution using the very simple things that we learned early on. Notice that this one is find the probability the mean height exceeds 66.5 inches. The key word in the problem is mean, because we're now looking at a sample mean. Here's the sampling distribution then of x bar. Here's the population distribution compared to the sampling distribution. At the Peanutty Peanut Company, dry roasted shelled peanuts are placed in jars by a machine. The distribution of weights in the bottles is approximately normal, with a mean of 16.1 ounces and a standard deviation of 0.15 ounces. Without doing any calculations, explain which outcome is more likely: randomly selecting a single jar and finding the contents to weigh less than 16 ounces, or randomly selecting 10 jars and finding the average contents to weigh less than 16 ounces. Here's what we could put as a solution. Since averages are less variable than individual measurements, I would expect the sample mean of 10 jars, to be closer on average to the true mean of 16.1 ounces. Therefore, it is more likely that the single jar would weigh less than 16 ounces than the average of 10 jars to be less than 16 ounces. Find the probability of each event described above. So if we let x equal the weight of contents of a randomly selected jar of peanuts, the probability x is less than 16. Again, the last example we used table A. This one I'm using the graphing calculator to show you the different ways to solve it. We can use normal CDF, use a large number. We've talked about negative 100, quite a bit in here, comma 16, and then 16.1, which is the mean, and then 0.15, which is the standard deviation, so 0.2525. Now we let x bar equal the average weight of the contents of the sample of 10 jars. So to find this, we have x bar 16.1 is still the mean of x bar. The new standard deviation, we take 0.15 divided by the square root of 10, which is our sample size of 10 jars. Probability x bar is less than 16. We use normal CDF, negative 100, 16, 16.1, which is our mean of the x bar, and then 0.15 over square root of 10, which is the standard deviation. So we get 0.0175. This answer agrees with the answer to part A because the probability is much smaller than 0.2525 that we got originally when we were looking at the individual versus the 10 jars when we average them. Most population distributions are not normal. What is the shape of the sampling distribution of sample means when the population distribution isn't normal? It's a remarkable fact, as the sample size increases, the distribution of sample means changes its shape. It looks less like that of the population, and more like that of a normal distribution. When the sample is large enough, the distribution of sample means is very close to normal, no matter what shape the population distribution has, as long as the population has a finite, meaning that number ends, standard deviation. Draw a simple random sample of size n from any population with mean mu and finite standard deviation sigma. The central limit theorem says when n is large, the sampling distribution of the sample mean x bar is approximately normal. How large a sample size n is needed for the sampling distribution to be close to normal depends on the shape of the sampling distribution. More observations are required if this population distribution is far from normal. Consider the strange population distribution from Rice University Sampling Distribution Applet. Describe the shape of the sampling distributions as n increases. What do you notice? If the population distribution is normal, then so is the sampling distribution of x bar. This is true no matter what the sample size n is. If the population distribution is not normal, the central limit theorem tells us the sampling distribution of x bar will be approximately normal in most cases if n is greater than or equal to 30. Here's a population distribution with a strange shape. What do you think the sampling distribution of it will look like for a sample size of 2, 5, and 25? Again, no matter how strange it looks to begin with, if we get a sample size, as the sample size increases, it actually would look more like the sampling distribution of a normal distribution. So here are the results of 10,000 simple random samples of each size. The first graph has 3 peaks. Since there are only 4 basic outcomes for a sample, 2 small values, which gives a sample mean, 2 large values, which gives a large mean, or 1 of each, which gives a mean in the middle. Since there are 2 ways to get 1 of each, the middle pile is roughly twice as big. So here's what the distributions would look like for n equals 2, n equals 5, and then when we get to n equals 25, we can see what happens to the distributions. Based on service records from the past year, the time and hours a technician requires to complete preventative maintenance on an air conditioner follows distribution that is strongly right skewed and whose most likely outcomes are close to 0. The mean mu equals 1 hour and the standard deviation sigma equals 1. Your company will service a simple random sample of 70 air conditioners. You have budgeted 1.1 hours per unit. Will this be enough? Since the 10% condition is met, there are more than 10 times 70 or 700 air conditioners in the population. The sampling distribution of the mean time spent working on the 70 units has mu of x equals mu, which is 1. Sigma of x bar is sigma over square root of n, which equals 0.12. The sampling distribution of the mean time spent working is approximately n 1.12, with n equals 70, which is greater than or equal to 30. Here's our distribution. We need to find the probability mean time is greater than 1.1 hours. So we find the standard value. 1.1 minus mean mu of 1 over sigma of x bar, which is 0.12, equals 0.83. So we're finding the probability z is greater than 0.83. Remember, to find greater than, we take 1 minus the probability that it's less than. We look it up on our A table and get 0.2033. So if you budget 1.1 hours, there's a 20% chance the technicians will not complete the work within the budgeted time. Here's one more example. Suppose the number of texts sent during a typical day by a randomly selected high school student follows a right-skewed distribution with a mean of 15 and standard deviation of 35. Assuming that among the students at your school that are typical texters, the question is, how likely is it the simple random sample of 50 students will have sent more than a total of 1,000 texts in the last 24 hours? We state the problem first. What is the probability the total number of texts in the last 24 hours is greater than 1,000 for a random sample of 50 high school students? Now we do the plan. We have a total of 1,000 texts among 50 students is the same as an average number of texts, which is 1,000 divided by 50 is 20. We want to find the probability that x bar is greater than 20, where x bar is a sample mean number of texts. Since n is large, 50 is greater than 30, x bar is approximately normal. The probability of x bar greater than 20, on this one, again, I use the calculator, normal CDF. You can put in 20 and then up to a certain number. Now notice here, we're going 9999 because we have over 1,000 texts. For our large number, again, just pick something large when you're doing a greater than problem. Then we have 15, and finally, that's, remember, our mu of x bar, our sigma of x bar, we take 35 divided by the square root of 50. The square root of 50, because n, our sample size is 50, and 35 was the standard deviation of the right-skewed population that we started with. So our answer is 0.1562. So there's about a 16% chance a random sample of 50 high school students will send more than 1,000 texts in a day. Here's a review of what we've learned in this section.